Welcome all the three batches: manufacturing, mechatronics, and BST 2020 B2 semester 2 batch. For today, lesson 6, thermodynamics. Today, the date is 22nd January 2022. So, are there any more students to come? Because there may be one subject from 1:30 to 3:30 for manufacturing and mechatronics maybe. But I believe all join here today. Putala Hinode?
Yes, sir.
Okay, very good. Manufacturing ayavadu kohomada? BST?
Okay.
Yeah, manufacturing is here. Mechatronics. Okay. Today, lesson is a continuation of last week lesson. So today, we need to look into this 4 items. Of course, you have your one-time note. It's your responsibility to go through that. And our session is somewhat like an enrichment for the class for better understanding of the subject. Because you should understand the subject in your own ways. I may be understanding in my way, you should be understanding in your way. Others should be understanding their way. Okay, but the text may be the same, discussion may be the same. That's why joining the class is important. Okay, so no two persons are the same, so the understanding is different levels. So yeah, that is important. Okay, that's why we all have different ideas, different understanding, different knowledge, but the same subject matter. Interesting, eh? Expansion and work done. Last week, we have looked into this slide. I will copy that here. You can see that. During the work done, the piston moves means the gas here, the steam expands. When the steam expands, that pushes the piston and perform a mechanical work. Okay, that's why. So energized steam expands while moving the piston against the load. So yes, energized gas molecules deliver a work transfer from the system to surrounding. So energized system release the energy and delivers the work, and this energized steam expands. That's the point. When it expands while moving this piston, yes, this steam performed a work. Okay. Same way, let's say this is an IC engine. let's say IC engine power stroke. Let's say petrol engine, you know better. Or diesel engine, okay, power stroke. Power stroke means, so energized gas. So de-energized, energy released, the same gas. Okay. Same applies. Energized gas molecules deliver work. Means work transfer from the system. Outside the system is surrounding. That's it. System to the surrounding, outside the system. So from the system, work is delivered. So internal energy initially is U1 at the state 1. At state 2, it is U2. So U2 becomes, you have then internal energy U1 minus the work delivered to outside. So W is the work done. Okay. So if E2 and E1 are the energy levels again, E2 is E1 minus the work done by the system. Sorry, work done by the system on the surrounding, or work released by the system. Yeah, work done. So de-energized, energy released. Actually, release means this is a way of energy transferred mostly to the work. So I will take the word energy released here out. Okay, I just cut it off. Because, yeah, system really just releases energy. That's true. So it transferred into the work, transferred from the system to the outside. System losses energy. So this energized gas expands again. Sometimes when I'm explaining too much, that may bring confusions, but please, I'm repeating the same, that this energized gas to deliver a work, this gas should expand while moving a mechanical part. Okay, nice. So energized gas expands. Okay, so next topic here is the same. Energized gas expands. So I'm writing this as expansion. Okay, expansion. So we'll see. Just for your memory. So I'm taking, instead of 2, I'm putting this piston here. This is the state 1 position. One position. This is 2 position. Okay. So the force F, yeah, it's here. So don't worry. Yeah, good. I hope you may understand this very well. You are too early to send the attendance. Huh? So expands means if I take the piston movement, please no need to send the attendance now. Huh? Attendance event hadis වෙන්න එපා. Piston displacement. This axis. So expands. One is here. Okay. One is here. There is a certain volume here. You can see. The piston moves because the energized gas makes the piston move. Because no choice. Piston has to move to give the way to this energized gas to expand. Expanding means it is the gas looking for more stabilized conditions. So energized means it is not the stabilized condition. It is not the stable way. It is not the natural status of the gas. Energized means it is looking to release the energy. That is the nature's way. Okay. It's trying to release the energy and merge with the nature or the surrounding. So in order to energize this energized gas to release the energy, that expands because it looks for that. If no chance to expand, even there can be a possibility of rupturing this. Somehow look for this neutralizing. So this one. So carefully crafting this solution to let the energized gas expands, making the piston move, delivering a work, turning a wheel, and make the bicycle move forward. Okay, so initially at 1, then finally at 2 position. Interesting. So here 1, piston 1. Sorry, piston and position 1 means there is a volume. I just put V1, the volume at the piston position 1. Same way, when the piston moves to the end, let's say, moves till the end, expands means increasing the volume to 2. Okay, 2. Interesting. And here, there is another parameter. You know about this parameter from your school time. Pressure. Even in your physics, maybe semester 1, you may have learned this physical parameter pressure. So there is a parameter called pressure. Okay, so you may have some understanding of pressure. So I'm not discussing pressure at this time, but I'm going to say one thing about pressure. In gaseous substances, let's say in gases, the simplest way, pressure and volume parameters are going hand in hand. Not technical, but hand in hand. Hand in hand means interrelated. Interrelated. The nature's way. Okay. The nature's way. Pressure and volume goes hand in hand. Yeah. So pressure is somewhat like a solidity one way. One way it has a potential to work done. Okay. So you can understand or you can look at the pressure in different ways. Okay. So this pressure like quality in gases it is quite natural. Okay. And I just put in this way. So I no need to write the technical words. Pressure. But I denote in the symbol P. P. Small or simple P. This is the symbol or this is how we denote pressure. Volume. We can say volume. Big V and small v. If 1 kg, we use small v, means a specific. Or else, for a given mass, it is v. Okay. And the initial state we call 1. V1 is the volume. State 2, V2. So here, you know that as pressure and volume in gases, surprisingly, interconnected. So this nature interconnection, we represent it in a graphical way as a PV graph. So PV graph or PV curve. So one axis is pressure. Okay. One axis is pressure. So the other axis is volume. Okay. So pressure may have standard units. Volume may have standard units. So you can see the volume is related to the space this gas is being occupied. So initially V1, start the piston to move, means expanding this volume, and finally change this volume to the level 2 we call V2. Okay. So then the pressure. So initially there may be a certain pressure level. So just take P1. So P1, V1 belongs to the initial level, P1. Interesting. Eh? It is quite interesting. So nature's behaviors we are observing and representing with our something like a physical understanding. So we are representing this graph. P1. I think in your smart device, you will be able to see this. V1. So there can be temperature as well, but I just put only 2. P1, V1. And there can be corresponding temperature as well. So later we will discuss that. Another one, when this moves to P2, 2 level, the pressure drops. The volume or the space the same gas occupied increases. Okay, interesting. Okay. So this is P2 corresponding V2 volume. So expansion is from V1 to V2 is the expansion. While the pressure reduced, this is natural from P1 to P2. Okay. So then you may have a lot of intermediate states. See. So 1 to 2, this expansion. So this gas passed through these intermediate states. Okay, these intermediate states. I can mark it. Likewise, intermediate states. And the corresponding pressure levels. Also possible. Imagine naturally and practically. So this will be like this. So it is something like a curve. Okay. It is something like a curve. So even you can have intermediate states. So if you imagine this nature of so many intermediate states, so that the corresponding point here you can see the pressure levels and the temperature levels. These are something like coordinates of this PV coordinate values. I just take only one. and I just denote this as P. And at this piston general position as V. So this nature of P and V, you can see. Many such points. Okay, good. And even 1 to 2, this changing of PV, there is a kind of continuity. Okay, there is a kind of continuity. No, sorry. Let me try to draw. Yeah, nice. Okay, so now you know that this PV curve is nothing but the expansion of this energized gas. PV curve is nothing but the expansion of energized gas. So P reduces, V increases. So expansion, this is the way this PV change. Okay, and then that's why I mentioned that P and V goes hand in hand. So we have to look into this, how this P and V is changing. Of course, T also have a connectivity. Even P and T we can draw, but let's say P and V goes hand in hand. So if you need temperatures, fine. You can have temperature as well here. P, V, only PV shown, but temperature also here. You can consider it, but only the P and V is shown here. So at this point, T1, V1, if you need corresponding temperature, that is T1. So in a proper way, this all putting as subscripts. Can you see? This way. P2. V2. And T2 is here. Okay, good. And if you need to look into this P1 V1 to P2 V2 change, of course, the change is from 1 to 2, 1 to 2. So here also from 1 to 2. This is state 1. This is state 2. From 1 to 2, this process takes place. So there is a direction for this. So if we need a direction, fine. Sorry. We can just mark a direction. This is the direction. 1 to 2. Okay. Not 2 to 1. 1 to 2. It's expansion process. So when you experience the expansion of energized gas, only energized gas expands. Or if it sees, or if the gas sees a low energy level positions, the gas will change into that level. So it is changing state, we call, changing high energy level state to low energy level state takes place. Okay. That's how the gas flows. Low pressure, low temperature. Zone is being formed. So the higher pressures, higher temperatures, let's say higher pressures in general, flow towards the low pressure. So that's how it's taken place. The flow of high speed winds and all. Okay, hurricanes or cyclones, because of this low pressure. Okay, so low pressure has less energized. High pressure has more energized somehow. So it is trying to neutralize, comes for a balance, natural balance. So there is a flow. Even in the nature, there are similar engines takes place. Engine performance, like there are nature's way of performing this nature of this kind of thermodynamics engines. Later we can learn. Okay, so this should be something natural to you. This takes place. Confined gas at state 1. Now we use the word state. That condition, pressure, volume, and temperature is energized. Then it's looking for neutralizing low energy levels. So it sees it's easier to push the piston boundary towards the end. Yeah, gas expands. But in return, we are taking a work done. See, gas doesn't know that we are taking the work. Okay, but gas performs. We take the work. Yeah. So gas performs naturally. So we are taking the benefit of that expansion. Actually, gas is looking for to neutralize, to merge with the nature. That's why it's going to the exhaust finally. Exhaust is the surrounding is the nature. Okay, good. So we are benefiting, we are tapping some energy out of that work done. Same in the waterfalls. Sometimes we do electricity generation. What is falling? Because it's looking for the stability, it is looking for the sea, the lower levels, from the above sea levels to the lower sea levels, the gravitational lowest levels. So water is flowing. So we are putting a mechanical device. Let it turns and we take electricity or we run machines. The same thing. The energized gas looking to neutralize. We are making use of that. Even energizing the gas we do for this purpose. So gas is a working fluid. Okay, good. I hope you can understand this. That's how the PV graph came into life, because P and V, we can physically feel and see this. Same way, T also reduces. So P, V, and T, there is a connectivity. So other than knowing PV, PVT connectivity, we have to understand. PVT connectivity means in maths, function of PVT, if you take PVT as parameters, we have to look into the function of PVT. Actually, I'm neutralizing your knowledge, naturalizing your knowledge. I believe you are looking into your one-time note. So function of PVT. So function of PVT is common for all the points here. Function of PVT, the connectivity, the parameters, the link, the connection. Okay, that's what we call the gas laws. Yes, gas laws. Laws means, law means it won't change. So these are nature's ones. The relationships, people found those gas laws. We are going to learn this as well. Very simple. So gas laws, knowledge we can have. Then we can have a good understanding about the intermediate process as well. Okay, intermediate process as well. Even the temperature set, the intermittent levels of expansions, we can look into that. So this is a very nice slide. So I believe you have to have a total understanding. Pressure P and the volume together. Temperature is always there. If there is a matter, there is a temperature. If there is a matter, there is a volume. And of course, if the matter is in an enclosure, of course, there is a pressure because that is related to the molecular mass movements. Energy also one way, molecular mass movements. Pressure is another way, molecular mass movements, but related to boundaries. This P makes the boundaries of pushing. Okay. P makes the boundaries of pushing. But gas has so much of power because of this higher P levels, because of the high kinetics. But the gas molecules working together never destructed each other, but they can destruct, they can rupture the boundaries, they can rupture the cylinders where the gases are enclosed. Interesting. So this P, V, and T, quite natural parameters the gases can have, any gas can have. Quite interesting. Then gas laws. There are gases we categorize in this way. Ideal like gases. So there are ideal gas laws. You will learn that. Ideal means it's mostly conceptual. They're assumptions. And there are real gas laws. And for real gases. Example for nitrogen, there can be FP, the function of PVT or PVT connection. For nitrogen, oxygen also there can be a PVT connection and there can be a little difference. If there is a little different, generally it has to be because different molecules, okay, nitrogen and oxygen. So nitrogen related gas laws or connection of PV and T for nitrogen is different from connection of PV and T. But some gases like hydrogen, helium, or high temperature nitrogen, or high temperature oxygen, or low pressure nitrogen, oxygen. So there can be situations that real gases can be considered as ideal. So scientists, they did experiments, they observed this and they found this and give it to the world for the benefits to the world. So we are using this nature's phenomena with this knowledge of this scientists found ones to find solutions for day-to-day applications. Okay, this is not for you to memorize, but for you to understand and do something for the society. This is not for you just to pass the exam. දැන් මොකට හිතාගෙන හරි වෙනස් විදියකට සහතිකේ ගන්න පාඩම් කරන්න මේක පාඩම් කරුවට පුළුවන් වෙන්නේ you have to understand this. Okay, you should understand. Then to understand you have to receive the knowledge, try to understand, then try to apply this. Imagine about the knowledge, imagine your understanding with some interest to do some creativities and all. And finally, you can apply this on real world applications. That is very important. If you are looking for the memories of this, there is no value. Okay, so you should take note that. Yeah. Okay, that is very important. So this slide tells a lot. Expansions. But there are some mechanical movements are involved with this expansion. Okay. Mechanical movements are involved in this. There are a lot of applications of this. We'll go for another one. I will try to take this. Yes. Same. Initially V1, finally V2. Same like this. See, finally V2. So see the shape, because this gas expands. Here, the difference is this one state gas, here it is there. But here, state one gas moves this way. Until I think I should take not this, but this as a picture. Let me take this. Sorry. This is a master slide, it seems. Yes. Now, okay. V1 is here. V2 is here. Nice. It's nicely coinciding. Yes. Okay. Good. So 1 and 2. And you can see different states like this. So whatever comes here at 1, the pressure and temperature volume is here, of course, certain temperature levels. Volume increase means the gas expands. Pressure reduces. So you will see this nature of connectivity as well. So I don't see any difference here. Nice. Okay, very good. Let me group this. Interesting. Okay. So again, it's the same. It's the same. But when you evaluate the work done in this piston cylinder systems and in the turbine systems, it is different. But still you can see this PVT nature. Okay, that is very important. So no matter it's a turbine, it's an engine. So you will see this. You will notice this. Quite interesting. Okay, the nature's works. So the nature's work we are crafting for our usage, but the nature works, nature's phenomena. Okay, good. So all relevant. I feel still. Good to keep this text. Still too early to send the attendance. Okay, why worry about the attendance that much? So your presence is appreciated, then I will give you time for that. Or if I forget, just before closing down the winding up the class, you can send it. Okay, don't worry. Nice. So this expansion here through the turbine blades all turns and produce a work here. But here it is turning, rotation here. Here it's a displacement. Of course, gas displaced, here also gas displaced. Because after that, new gas is coming here. Here also new gas is coming, but here linear work, here rotational work. So that's the difference, okay? So here it's a rotational work. Understand? Give me a second. Yes. Didn't work out. Yes, at least. The rotational work here. So if it is F here it is a torque. Okay. So that's how we are making use of this mechanisms. Anyway, it's a power again because of the expansion of gases. Even for steam expansion, it's the same. Still, you can have PVT. So I will take one more slide here. So one more addition. This turbine we call, because you can see in and out. Okay. So we call it's an open system. During the power delivery. And of course, it's always open system, an open system. And there is a flow of steam or gas throughout, through the turbine. So we call a flow system. flow system. So there is a flow through the system, and if it is running steadily, we call steady flow systems. But anyway, it's an open system. Interesting, eh? Interesting. This is an open system. The same way, if you look into this piston cylinder arrangement, you can see this is a closed system. Oh, open system. 2 times. So this is closed system. Closed system. So no steady flow, so no flow. And this has closed means this has this boundary is closed, but one side is moving. So moving boundary and closed. If no moving boundary, no chance to expand. Okay, no chance to expand. So quite interesting. It's very interesting. Good. So the PVT and this PV diagrams, connectivity with the gas laws and all, you know this now. So outlet of this, if you really look into 2, surely this 2 is, even I can put it here. 1, 2, V2 is the same. Okay, good. So with this understanding, you should look into your notes. Okay, you should be looking into your notes. Good. the balloon. Okay. Also, there is PVTs connected. Very nice. So here, closed system. You can press the balloon, but if you take this balloon and try to press it, you feel the force, the resistance from the balloon. You feel the resistance. You cannot simply press this. Okay. And you can imagine the molecules there moving and hitting around and keep this shape of the balloon as it is. See the power of tiny molecules working together as a single entity. Even you cannot press the balloon. See the power of molecules working together. Now, normally a normal temperature, you cannot press the balloon. So here, you know that, yes, pressure. You feel here the pressure. Volume is there. Temperature is here. Other than that, there is some mass. Air inside or a gas inside, that's a mass of that. Okay. So FVT, and more precisely, you have to add mass as well for the gas laws. If not mass, there should be this V as the small v, means per unit mass, the volume. Then you no need to have this. But there is a separate connectivity that M and V, this M and V has a connection. This M and V has a connection, that is this M divided by V. Sorry. This V divided by M as a single parameter other than the pressure, small p. See, connected. So V by M. So this V by M is what we call the specific volume. So In the gas laws, you can have P small vt or PVMT, because the volume, mass, pressure, temperature, all together. But the gas laws are there so that only two parameters, if you know, you can understand the others because of the gas laws. So talking about the gas laws is not today one. So that one we will discuss later. So this PVT is interesting. Also, you imagine temperature. It's of course great. But imagine P and V existing together in the balloon. How nice this, how wonderful. Together existence. Yeah, this is together. So you cannot talk only about volume without pressure when it comes to gases. Very interesting. That's why this graph. Oh, sorry. Becomes very important. This becomes very important. Oh, sorry. Very important. So PV graph is very important because this shows the expansion. Okay. This shows the expansion. So I put the balloon aside. The balloon has no much relationship here, but here got. Here maybe I will take the balloon out. I better keep it here. Very important. Okay. The expansion. Of course, energized gas, relatively energized gas expands. Expansion. Okay. Even this balloon is energized. That's why In any case, if you open here, this balloon moves as well because this gas energized. That's all. So very interesting. Today, I didn't talk about the enthalpy yet. Expansion and work done, relationship, the connectivity I have shown here. Okay, but this beauty of PV, P and V, connectivity is very important. The PV connectivity is here, P and V. Okay, P and V. So later we will see what P and V connectivity is. Okay, what P and V connectivity is. Let's say here, not bringing some maths here, but I'm just drawing a line. Let's say this is the average line. P average. P average. P average. Let's say PA. A is average. The P average. And the expansion is from V1 to V2. So the expansion is V2 minus V1. This is the expansion. So later we will see how we take this average. So it's a different story. Later we'll take how we take the average. And if this is the expansion, means the increase in volume. Or expansion. Is this. So increase. There is a symbol we call delta. Delta means generally we use the word delta for change, but this change we consider as an increase. Okay. And then if you think of this PA times delta V, PA times delta V, so that is same as PA times V2 minus V1. Okay. So this is equivalent to the work done by gas. Okay. During expansion. This is very interesting. Later I will explain you how this average pressure times the expansion or the volume increase become work done by gas. Of course, you have to have the mechanical device to tell. If not, it's a different story. Then this PV is different. So what happens if no turbine? It is something like a nozzle. Okay. So nozzles are be used in the propulsions. Even in aircraft engines, you can see both turbine and nozzle parts. Interesting. So you have to take note this. So when we, today I will send the same one day, the daily note. So you go through this and have your own understanding. Okay. You have to have your own understanding. I will let a little bit only today. We call this turbine engine or jet engine. So you can see the combustion. You have a turbine. Then after the turbine, there is a nozzle part. So turbine generates some power, mechanical power, to run this compressor component. Later we will learn more about this, but I just mentioned about the compression in a different manner. So then after compression comes for the combustion, and the fuel comes here as well. So energized gas passing through the turbine. Okay. So partly because of the turbine generates some work, other pass through the nozzle as a jet stream. Because of this jet stream, this engine propels. We call propulsion because of this jet stream. So there is a turbine component and there is a nozzle component. Okay. Nozzle component as well. So together perform the power generation and the propulsion. This part. The power generation and the propulsion. Okay, good. So next week we will learn more about the processes, this PV diagrams, and a lot to know, but let me conclude the class today that now the time of our lesson changed from 1:30 to 3:30. So very interesting, these applications. You can see so many images. So this knowledge all will be familiar to you afterward. So all should be applicable. So aircraft engine, true, but the same turbine engines we can use for power generations. Okay, the same turbine engines we are using for power generations. So even if you get an opportunity to work for developing the turbine engine, sure you will perform. This is the turbine engine, this one. So it's everything the same principle. So even you can think of developing turbine engine for small power generations. You can use turbines. Turbines we can easily develop. If we can develop locally, we can use not for the aeronautical, but for power generation applications. Gas turbines. You can use. Interesting. Okay. you can develop. So compressor component to make the air compressed. That is the opposite of this P2 to P1 like this, compression. So you are squeezing the air, then mix with fuel, burn here. So the way it is managing the flow and the pressures, this pushes through the turbines and generates some work done and partly a jet stream. Okay, a jet stream to propel this. Okay, so this all the related applications. Similar turbine is here. Okay. But here this can be a steam turbine. So high pressure steam comes here, and then the low pressure steam de-energized, less energy, the steam with lesser energy, leave the turbine, turning this. So aircraft turbine engines, other than the turbine, there's a combustion component and also compression component, and there is a propulsion component at the exhaust. Okay, nozzle component. Interesting. So try to connect the theories for practical applications. Okay, very interesting. So other than that, today, what we have discussed, lesson 6, start from here. See. Paving tractor came alive here. Okay, come to life. You see the importance of PVT connectivity. Expansion. What expansion means? It's here. See turbine, it's turning. Here in the piston cylinder, it's linear force. It's the same. But this is open system turbine. This is closed system. But the same phenomena applies. But for calculation, there can be different applications. The balloon, similar way. You have the PVTM system. So PVTM systems. So instead of V and M, you can have the small v in this. Then we have PVT system. So P and PVT are intensive properties. You check your notes. Okay. The PVT, intensive properties. Check in your notes. What are the intensive and extensive properties? You one time not mention this. So you have to go through this, because if I'm going to teach this all that what is in your text notes, you will not learn thermodynamics. So I will leave that part to you. So understand this very well. Yeah. So these are your responsibility of learning this. Okay, it is very important. Good. So basically, you're okay with this. Then finally, we learn the work done is something like pressure times the expansion. See, so when the work done has a connectivity with pressure and expansion, so high pressure, very important. When high pressure, temperature also high pressure. And with high pressure, we can go for bit larger expansions. That's why the turbine technologies with the new material developments nowadays, especially in the aircraft industries, the aircraft turbines are more energy efficient now because they can withstand for very high pressures. Yeah, because very high pressures, temperature also I see PVT connectivity. Then you can have better expansion at high pressure side. So somewhat compact, but P times V, delta V is a big one, relatively big. So probably the lesser energy, bigger work, means efficiency very high, relatively enhanced efficiencies. So there's some little applications. So have some interest on this. So for small power generation, you can construct one for low temperature. Very nice. Low temperature turbine. Okay. You can develop it. You can design. You can try. That's how people are moving forward. Countries are moving forward. We never say cannot. It's possible. It's the art and craft of developing engineering solutions. Okay. That is very important. නැත්නම් නිකන් පොතක මෙමරි එකක් තියාගත්ත දැනුමක් කෙල බින්දුවක් තරම්වත් වටින්නේ පුතා කිසි වැඩක් නැහැ. So you have to go for this extra to connect your knowledge with some practical aspects. That is very important. And look for some creativities. Okay. So that's all for today. See you next week at the same time. So I couldn't give you assignment these days, but don't worry, you go ahead with exploring of knowledge, thermodynamics. And also I will create a Google Classroom and I will send it to you. I couldn't do that because little bit busy these days. Anyway, soon I will send it for you to upload to CS. You respect your continuous assessments. You respect your notes and videos. Read and understand and have your own understanding and your own knowledge and creativities. That works for you. It's not about the certificates. Okay. So in your exam paper, other than the thermodynamics questions, I will be putting one question. Thermodynamics, but related to socio-economic environmental aspects. Okay. Thermodynamics with socio-economic environmental. Because now we are learning subjects, but we are not good overall looking at the things. That is really bad. So starting this time, additional question, a very serious one about the nature, environment, sustainability, and even economics. So how the thermodynamics play a role. So you have to explore this. Okay. You should get ready for that question by yourself. Yeah. So definitely one question I'm putting because learning just pure subjects so far didn't work. We have to look into overall to improve ourselves. Okay. Later we will discuss such nature of subject matters when we find time after looking into these technicalities. Thanks, Putala. 3 minutes I took extra. So take care all of you and thanks for joining the class today. And I'm expecting more participation. That is very important because 2 hours, if you cannot spend these 2 hours, because we are trying hard, we are sacrificing our time. So if you are missing the class, I think you should not get chance for the exams or anything, because you should respect the class. That is very important. So joining the class is very important. Okay. So whenever the class is there, you should join. If not, you should send the apologies before the class that I could attend because of this. Simply not attending the class, we cannot accept, because that's for your betterment. Okay, good. Thanks, Putala. Then take care, all of you. Omicron, I don't know, Corona is increasing now. So you have to take care, you and the others as well. So be responsible. So also have good health and good luck. See you next week, Putala. So I'm going to stop the class. I will send this daily note to you afterward today in 30 minutes time. Any questions before stopping? Okay, then. See you next week. Bye.
Thank you,
sir.
sir.
Thank you, sir.
Thank you, Bhutan.
Thank you very much.
Thank you very much, sir.